Hi, the next video in chapter 2 is going to talk about projectile motion. And then we have a pretty standard problem here of an object fired at initial speed 30 meters per second at some angle above the horizontal. And then we want to see where it lands. So it's going to land on a cliff that's 10 meters high. And we want to find out how far away in the horizontal direction from where it was fired did it travel. Okay, so this section just picks up off of last time where we talked about general motion. And remember, the position of a particle has an x-coordinate and a y-coordinate, and this is completely general. Right, so we're starting with this, and then we're going to look at a special case of this. So now we're going to assume we're going to take the acceleration to be pointing in a certain direction. And actually, we're sort of specifying the coordinate system too, or at least we're going to specify that the y direction is going to point vertically upwards. Now, we'll explore this in a little bit more detail later on in the course, but for points near the Earth's surface, so even a mile or two, a couple miles above the Earth's surface is still really close to the Earth's surface compared to the radius of the Earth. For points near the Earth's surface, the acceleration due to gravity is approximately constant. So you drop a bowling ball, you drop a tennis ball, it doesn't matter, the mass of that object. It will fall with acceleration that's a certain value. So it's going to point vertically downwards. So it's going to point in the negative j direction. So we have negative g, which is going to be the magnitude of this vector. So this is pointing in the negative j hat direction, or negative y hat direction. And so this is approximately 9.8 meters per second squared. So this is an experimental fact. So this means that every second object gains speed at a rate of approximately 10 meters per second per second. I think it's around 22 miles an hour per second. So imagine you drop a car off a cliff, and if you can ignore air resistance, then in every second it's going to gain speed at about 22 miles an hour. So after 1 second, it's going 22 miles an hour. After 2 seconds, going 44 miles an hour, etc. That's what this means. So this section is just exploring the consequences of this. We're taking our general equation of motion and seeing what happens if this is the case. So I want to emphasize the fact that the equation for motion, the equation for position as a function of time, remember that we can treat the x and the y pieces completely independently. Right, so I want to talk about the I direction separately from the j direction. I probably should be putting I dot and then a hat, but I'm lazy. I just write the I and then the hat. So the given information that we have is ax is 0, the x component of the acceleration is 0, and the y component of the acceleration is minus g. Okay. So g is called the acceleration due to gravity. It's in parentheses, it's like the magnitude of the acceleration due to gravity. So just remember that every time you write g, that's a number with units, but it's positive. So if you want that thing to be negative, you have to stick the minus sign in front of it. So I don't have to write down meters per second squared, because that's built into this quantity g, but I do have to write down the minus sign to specify that, given that the y direction we're assuming to be vertically upwards, we have to say that, well, no, acceleration doesn't point vertically upwards, it points vertically downwards. Okay, so let's look at the left-hand side. The left-hand side is easier. So remember, velocity is the integral of acceleration. So the integral of 0 is a constant. So the x component of velocity is a constant. It's not going to change. And then the integral of a constant is that constant times time. Right? So delta x is vxt. And this is basically like the only equation in the x direction that we're really going to need. So it's understood here that v initial, the x component, and v final, the x component, they're the same because v is constant. So notice how I didn't write v initial and v final. So in principle, they could be different, but remember, there's zero acceleration in the x direction, so they're actually the same thing. So we're just going to call this thing vx. So there's no need to call it v initial x or v final x, because it's always going to be the same thing in projectile motion. So shorthand, we might just call it vx. Notice how your book is calling it v naught x right here. So I'm just kind of reducing the number of subscripts because we don't need it, right? V naught x and v final x will be the same thing. So I'm just clearing that up right away, just to clean up the notation a little bit. Okay, so the y direction though. So now when we integrate this, we're going to have the velocity is, so the integral of the acceleration, this is going to be minus gt plus the initial velocity. So this is like that constant of integration. So when you plug in t equals 0, you get a velocity that's equal to whatever it started with. So you could think of this as it's the integral of a constant is a constant times time plus a new constant, c2. And then C2 needs to satisfy the boundary condition, the initial condition that the velocity is v naught. The y component of the initial velocity is v naught y at t equals 0. So this equation should look familiar. Remember, so I'll point out before. So remember we had v final is v initial plus at. Remember that was one of our equations for 1D kinematics under constant acceleration. It's the same exact thing here. It's just that equation, but plugging in a equals minus g. So maybe just to rewrite it so it looks like this form, which you're maybe more used to. I'm just going to reorder it. So it's v naught y minus gt. So we're just plugging in a equals minus g. Now keep in mind here that it's just the y components. So there's absolutely no reference to anything that's going on in the x direction in this whole equation. And that's exactly why, we've separated it like this. The left-hand side is only the x direction, only cares about what's going on in the x direction. This over here only cares about what's going on in the y direction. The only variable that appears in both is time. All the other variables are different between the two. So I'll write that down in a little bit, just to emphasize, because it's super important. Okay, so integrating this again. So this is like velocity as a function of time, is this thing. So if we integrate again, we get x as a function of time. So taking care of the constant of integration, we can say delta x is, and then integrating this with respect to time is v naught y times time. And then integral of t to the first power is going to be 1/2 t squared. So this is going to be a minus 1/2 g t squared. So again, this should look familiar, because this is just like the delta x equals v naught t plus 1/2 a t squared. Right? This is that equation from the 1D kinematics. Except again, instead of v naught, we have to specify it's just the y component. And instead of acceleration, we have to specify it's the y component of the acceleration, which is minus g. And obviously, this isn't the x direction. This is going to be the, ooh, that's bad. Remember, this is only what's going on in the y direction. That was a mistake, but a good mistake, because I can point it out. So when we did 1D kinematics, we didn't really care what that direction was. We just tended to call it x. Here we already specified the coordinate system, and vertically upwards is definitely a different direction than vertically downwards. So we're definitely going to stick with y for this one. Right. So you should look familiar. This is just like equation 1 from before. This is just like equation 2. So you could probably guess what the other two relevant equations that you might use are. It'll be equation 3 from last time. So that was delta y is going to be the average velocity, but just the y component of the average velocity times time. And this is v naught y plus v final y over 2 times time. So it's equation 3. And then the last equation, remember, is the one that doesn't involve time. So the fourth equation would be v final y. Remember, these are just the components. All of these equations are not vector equations. They're dealing with the various components. They're scalar equations. Equals v naught y squared. Now remember, this is plus 2a delta y. But a is minus g, so I'm going to do minus g 2g delta y. And there's nothing else interesting about Vx. Right? So you can imagine all of these equations for x. Like instead of y, for all of these y's, imagine you put in x. None of these equations are really all that interesting because when you plug in a equals 0, like this equation is just going to say that the speed, the x component of the velocity is going to be the same. So v final x equals v initial x. That's all equation 4 is going to say. This one, equation 3, if you plug in the same value there, you just get delta x equals vxt, which is the boxed equation on the left. For the right-hand side, if this is 0, again, you get delta x equals vxt. And then vx equals vx. So it's the same equation over and over again in that for the x direction. The only sort of non-trivial one is the y direction. Now there's a point that I wanted to emphasize here. The only variable that appears on in both of these is time. Right? So the x and the y directions are completely independent other than time. So time is the only thing that appears in both. And so you can actually say some interesting conceptual things based on this. So a quick example before we do the original problem. Suppose you throw a ball to the right and then you drop a ball from rest. So you drop them at the same height, and then they're going to travel the same distance to the ground. So both of these, both balls have. So we're going to say so actually, let me specify that this is the initial moment. The initial is what we just drew. So like for ball 2, the initial velocity is to the right, and for ball 1, the initial velocity is 0. And then the final moment is when they hit the ground. Final when ball hits the ground. So if we were going to set up some kinematics equations to find out the time each one takes, both balls have delta y equals, so it's going to be final minus initial. So if this is our plus y direction, the final minus initial is negative. Right? From the initial to the final y coordinate, that's pointing down, which is opposite the y direction. So this is going to be minus h, if h is the magnitude of the height. Delta y equals h. Looks like both have v initial y equals 0. So even though the ball 2 is moving to the right, it has no component in the y direction. The y component of the initial velocity is 0. And then also both balls have acceleration equal to minus g. And you don't even need to write this down for projectile motion. It's just so understood that that's the way it is. The reason I'm emphasizing this is that, so remember that I pointed out that if you have 3 of those 5 kinematic variables from the 1D, remember the 1D motion video? I pointed out 5 variables that all 4 of those equations have in common. And once you know 3, then you can solve for the other 2. So because these 2 balls have the same initial conditions here, they take the same amount of time to fall to the ground. So this is pretty surprising. A lot of people assume that, if you think about doing this, a lot of people will think that ball 1 will hit the ground before ball 2. So ball 1 is just going to fall right here. Ball 2 is going to undergo a parabola. So everything in projectile motion is going to undergo parabolic motion. And the way you could see that is if you track the position, it's a parabola. It's a downward facing parabola. It's concave down because of that coefficient's negative right there. And instead of t, if we replace, so t is proportional to x, to delta x there. So in other words, y is a function of x, which is exactly what this path is going to be. This is going to be like y as a function of x. It's a parabola. Any projectile motion has a parabolic motion if it's not just a straight line like for ball 1. So this is really interesting. I mean, imagine you drop a ball and you fire a gun at the same exact time. Assuming that the ground is flat and there's no air resistance, the bullet is going to hit the ground at the same time as the ball that you drop. Right? Even though it maybe travels a mile or two. It could travel. Whatever is going on in the horizontal direction doesn't really matter. That's what we're saying with these equations. The motion in the horizontal direction is completely independent from the vertical direction because the initial conditions in the vertical direction were the same for these two balls. When we solve for time, it's going to be the same thing. So obviously delta x for ball 2 is going to be very different from delta x for ball 1, which is 0. But they take the same amount of time. So that's the first interesting consequence of these. So your book does a pretty standard projectile motion problem. So I'll talk about what they prove in just a second. I want to do our example first here. Okay, so by the way, when we're remember that when we use our equations for our kinematic equations for constant acceleration, we have to have in mind what the initial moment is and what the final moment is. So here the initial moment is when the projectile is launched, and the final moment is when it hits the quote-unquote ground, but it's the raised ground, right? Hits the cliff. And the reason that's important is that's going to define the delta y. The delta y depends on where that final moment is. If you have your final moment up here at the peak of the trajectory, the delta y is going to be a little bit bigger. Right. Okay, so for the original problem, let's see what info we have. Looks like we know delta y is 10 meters, and it's positive 10 meters because we wind up at a higher point. So the final point has a higher y coordinate than the initial point. So delta y is positive 10 meters. Let's see what else. What else do we know? Now we're given the initial speed of the projectile. But the equations that we have deal totally separately with the x and the y components. So we have to split this initial velocity vector into the two components. And this is why we were talking about vectors earlier. Okay, so if this is 30 degrees and the magnitude of this vector is 30 meters per second, and this is v naught, and this is theta right here. Oops. Theta equals 30 degrees. So if that's the case, then Vx, you have to think about what trigonometric function is going to relate the adjacent and the hypotenuse. That's going to be cosine. Cosine theta is, let me break this up into two steps. Cosine theta is the adjacent, Vx, over the hypotenuse, over V naught. So solving for Vx, it looks like Vx equals V naught cosine theta. And similarly, Vy is going to be V naught sine theta. So Vx is 30 meters per second times cosine of 30 degrees. And V naught sine theta is 30 sine 30 degrees. And the reason I jumped over to the y component is sine of 30 degrees is easier than cosine 30 degrees. So this one, Vy, is equal to, so sine 30 degrees is 1/2. So this is 15.0 meters per second. Vx is equal to, so this is 30 times square root of 3 over 2, which is a little tougher for me. So let me plug this into a calculator. 30 times, looks like this is 25.98. I'm keeping one extra significant figure here in the intermediate steps, just to prevent rounding errors that propagate through with the calculation. So sometimes, you know, if you have a problem that has 3 significant figures, maybe you want to keep just 4 until the very end, and then you can round back down to 3. A lot of students like to keep 1,000,000 significant figures. You know, you don't have to keep 7 or 8 or anything. Just maybe one more than you otherwise would. It's fine. There's actually a mistake, or there's a potentially confusing thing because of what I wrote down. So try and pause the video and see if you can find it. So the thing is, I'll do another color just to emphasize this. So this is the initial velocity vector. It has magnitude 30 meters per second, but the whole thing is v vector. You know, this whole arrow is v vector. The x component isn't going to change over time. So the fact that we're calling it vx is kind of no big deal. But vy is going to change over time. So we definitely want to specify that this is the initial velocity and the y component. So really what we want to call this is the initial velocity vector, but just taking the y component. So I'm going to relabel this. This is v naught y. And this is to get it to look like, you know, what our equation's right here. It's v naught y. Notice how vy, just calling it vy would be ambiguous. We wouldn't know whether that's the initial or the final velocity. So we have to specify that we're talking about the initial velocity because it's vy is going to change over time. Okay. Now to solve this problem, it looks like we know a lot about the y direction. So we can actually, so our general strategy is going to be to use all this info. Maybe I'll do the strategy in red and then I'll go back to solving it in blue. So our strategy, use the y direction to solve for time, then plug into our x direction equation. Remember, time is the thing that's going to connect these two equations. Okay. So we're solving for time. We're given this info. The thing we don't have and don't care about is v final y. So that's going to point us to equation 2. So equation 2 is probably going to be the most useful one here. All right, so I'm just going to copy down equation 2 right here. So delta y is v naught y t minus 1/2 g t squared. Remember, this is positive 30 meters per second. V naught y is 15 meters per second times t minus 1/2 9.8 meters per second squared times t squared. So this is a quadratic equation for t. Quadratic equation for t. When you plug this in your calculator, you're probably, I mean, obviously your calculator doesn't know how to handle meters per second, so you can ignore the units for now and just know that as long as everything else is in SI units, your variable is going to be in SI units. So the calculator, what the calculator is going to spit out, or you could just use the quadratic equation and solve for the two different values of t. What you get is t equals 0.98 seconds and t equals 2.08 seconds. So let's go back to the picture and think about what these two solutions would represent. Okay, so all we said in the equations was that delta y is 10 meters. Okay, so that's this y value right here. This is the final y value. That's all we told the equation. And if you look at the arc, the trajectory of the projectile, it's going to cross that horizontal line 2 different spots, right? It's going to cross it here, and it's going to cross it here. So it's going to cross it at some small positive value of time. So notice how like t equals 0 is what we're calling the initial spot. So the first time is happening at some positive t, and then the final time, the other time that it crosses that is actually the one we're interested in. That's the later value of time. So what we care about here is the later value of time. This is the one where it lands. Now so we know what to do now because of this strategy. I want to point out one other small thing. What if this was negative? What if we had negative 30? Sorry, this shouldn't be meters per second. This is just meters for the delta y. If that were negative, then we would be solving for when the projectile hit, whoa. Sorry, this delta y should be positive 10 meters. Sorry about that. So what that would be representing is where the parabola crosses that horizontal line on the bottom right there. So looking at our parabola, so you would kind of have to go backwards in time. If you took the same parabola, you would have to go backwards in time for it to reach down there. And they would hit down there, pretending the cliff wasn't there, the cliff ground wasn't there. It would keep going like that. So if we plug that into a quadratic equation, we would get a negative solution for t. That would be this spot right here. That would be how much time before t equals 0, assuming it was following that parabolic trajectory. Right, the equation doesn't know that there's a ground right there and the ball can't have emerged from the from the ground, right? So the equation is just going to spit out a negative value. It's up to you to realize, maybe it didn't come from there. If we were originally on a cliff and it went down like that, this would be the relevant one. So we would choose the positive time. So you kind of have to think about the picture and think about why the t values from your quadratic equation might be spitting out those values. Okay, so our strategy tells us exactly what we need to do. Now we need to take this time and go to the x direction. So delta x is vx times t, and we already have both of those two pieces. 25.98 is that constant x component of the velocity, and then the time is 2.08 seconds. Meters per second times seconds gives meters. It looks like we get 54.0 meters. So this is going to be the range. This is our final answer. Okay, so the strategy is pretty common. You use whatever you have more information about, you use that to solve for a couple more variables, often time, because that's the thing that's going to relate the x and the y directions. Okay, so what your book does is it focuses on a problem where delta y is 0. So remember, in this problem we were given, the two givens were v naught and theta. So let me point that out here. So the givens here are v naught and theta. And we had a delta y that was non-zero, which is what gave us the quadratic equation that didn't nicely simplify. That's why we had to use the quadratic equation. Your book is focusing on the problem where delta y is 0. So see how the landing spot is the same y coordinate as the initial spot? So if delta y is 0, the equations simplify a little bit. And as a function of v naught and theta, and you're always allowed to use g in your answer, your book solves for that range. So instead of delta x, they call it r. So the final answer after so notice how there's no numbers plugged in. It's just left general in terms of v naught and theta. So we're imagining that v naught and theta could be any number that we're already given. So in reading this, you have to imagine that like v naught and theta are to be treated like numbers that you're allowed to use in your answer. So eventually, looks like the textbook solves for the amount of time it takes, 2v naught sine theta over g. So you might want to double check that this won't work for us because we have this different delta y, right? This will give a later time because it would be a parabola that keeps going. So you might want to double check that actually plugging in our value for v naught and theta, that you would get a time that's a little bit bigger than 2.08 seconds. So your book solves for that time for the delta y equals 0 case, and then the range. And it points out that the maximum range will happen when theta is 45 degrees. So you could prove that by taking a derivative and maybe setting it equal to 0, or just noting that sine 2 theta has to equal 1, so theta has to equal 45 degrees. Yeah, so then your book just talks about the solution a little bit. So that's definitely worth exploring as well. Okay, that's the end of chapter 2.